All right, welcome everybody. Hope it's been a great conference so far. Certainly has been for me. Very enlightening talks across the board. I'm gonna try to chime in a little bit here. Not being an MLE, not being an SRE, but an MLE, maybe a little bit out of my depth here with the technical details. But like, hopefully this is a useful conversation to have. All right, real fast about us. My co-presenter, Vina, unfortunately couldn't make it. She's out of London, and the flight schedule just couldn't work out with passports and all that. But she is a SWE here in Central Security, who did bulk of the heavy lifting from an engineering perspective on this as well. So moving on. So to start, the talk is going to be about like how do we apply AI for log analysis, and then we chose the UDAP or user data access policy as a very specific use case in which you can provide some good grounding around how you might use it to solve real business problems. But then the overall approach is not necessarily limited to just the UDAP use case, which is our overall goal as part of this R&D effort over the last couple months. So we'll start with the challenge of what the problem we're really trying to solve, and then our solution, and the overall high-level architecture, the results from from an ML and practical outcomes perspective, and what kind of lessons learned there might be, as well as like what are some of the next steps that we already have planned that may get some glimpse into the future. So the problem, I think not necessarily everybody here is familiar with the concept of UDAP or UDAP violation. So I'm going to kind of briefly talk about that. It's essentially, imagine a policy in place that your company may have that actually, in this case, Meta, basically says, yep, we need to be extremely careful about like accesses to user data. So any such violation will need to be caught with basically 100% accuracy, and we have zero tolerance when it comes to that. And so a potential way in which this might manifest is a employee John viewed the data 1, 2, 3, 4, 5. And some of the questions you may ask of that particular event is, okay, what data was accessed? What was data 1, 2, 3, D1, 2, 3, 4, 5? And why was this data accessed? Why did John have a legitimate reason to need to actually access that data? And if not, that is something is considered as a policy violation. So this is just kind of for a general grounding on what the problem space look like that we generally want to answer. So I'm going to kind of talk about it from a very high level, a globalized level scale of what are the challenges of applying AI in the LLM form, that is. Because AI as a field of study have been around for much longer than the LLM craze. But I'm going to use them interchangeably just because of LLM's a little bit tongue twister. And so the general application of AI on log analysis, all the way down to specifics of this particular UDAP problem, how it manifests in terms of its peculiarities and the challenges we need to address. So in general, for AI log analysis, I think one of the things that probably is no stranger to this group here, like logs are extremely voluminous, like highly voluminous, right? We probably have petabytes of logs in general for most of our companies that we have to plow through. And the signal to noise ratio on those logs is very, very low. So the things that you actually care about is maybe for a particular incident or particular event, it may only be like 50 logs out of the 50 trillion, for example, that you care about. So on top of that is, well, AI has a problem with context. It has a limited context window. There is an increase in context window these days to 1 million token plus with things like Mamba and Linformers and such techniques like that. And your Geminis of the world and Claude of the world also has a 1 million token context window now. But try to fit 5 terabytes of data into a trillion context window, that's probably not going to fly too well. Unless you have Silicon Valley, the show style of Wiseman score of 10,000 or something. And so that causes a problem, right? Like, how do I fit the right context? So thinking the needle in the haystack analogy a lot. So we have a planet full of haystacks, but then we have 50 needles we need to pull out. So which of the haystacks do I pick to even put it into the context window? To do that effectively is very hard, and oftentimes what happens is that we don't do it effectively if you just throw all the logs into the AI. I will talk a little bit more about that. We actually tried this and failed miserably. And so the other one is when you're looking at the data, that all the log we have, I don't know how many folks here have fully schematized all their logs. If anybody, I would love to talk to you. We don't. I found a number of companies, none of my own companies do. I had hundreds of customers, security clients of mine, that I don't think a single one of them ever did have 100% coverage in terms of fully schematized logs. And even if you did, oftentimes it's not necessarily very clear on what the content of that log even is. So because there are different ways to call things. You can call a host by their name, or you can call it by their full FQDN kind of name. You can call it by their IP address. Sometimes people throw that into the host field too. There's many different ways, right? There's a lot of ambiguity in terms of what the different fields in the schema might even look like, and inconsistency that exists there. And from an ML perspective, of trying to say evaluate, is my AI system for log analysis even working correctly or not, is how do I know when this is a particular problem I have? I want to identify incidents, but how many incidents actually happen? For security context, in security context, for example, the genuine incidents, knock on wood here and fingers crossed, we have very few in any given year, right? And in meantime, logs are turning. That petabyte of data every single day is not changing, it's still going. But we've had very few true ground truth label to learn from. And that's a perpetual challenge of applied machine learning in security domain, and I would imagine also in potentially in SRE domain too, as well. And then lastly, this is not an exhaustive list, by the way, it's just the things that I thought we've seen quite a lot. Lastly on this is hallucinations and overconfidence from your AI agents. How many times have you guys asked the AI for some questions, and then it was very confidently wrong? And it was just, actually I was talking to some of my teammates here. I was like, yeah, I asked my calendar agent to help me clear up my canceled events from my calendar so I don't see 5 overloaded event invites on the same hour. And it told me straight up, it's like, you don't have any canceled events. And then I'm like, I'm literally staring at one right now that's in the next hour. And I give it the example of that, and then it still tells me it's not canceled. The amount of gaslighting AI does to people it sometimes needs to be questioned and measured potentially. And in security domain specifically, we have an extremely low risk tolerance, right? Because a severe security event can actually be extremely detrimental. And this is oftentimes quantifiable by the amount of penalties you have to pay, and then also you will increase your cyber insurance. But let alone all that, it has a direct disruptive influence on your business operations, which is the almost unquantifiable amount of risk. So with that kind of high stakes, essentially you can't make mistakes. And guess what? In earlier talks by Michelle, I think it was quoted somewhere around 1.3% or 1.7% hallucination rate. That is not good when you are in an environment where you cannot make a mistake. So in a lot of times, you have to then effectively balance this the combination of automation and oversight by manual efforts. But the problem with that is manual efforts are extremely expensive. How are you going to validate potentially billions of alerts that is coming through the window, right? And it's kind of like when we're on call as an SRE in some cases. I mean, non-SRE also are on call as well. But when you're on call, you just keep on getting alerts that just called in the middle of the night. You're like, man, this has nothing to do. This is not a problem. This is just a false alarm. Can we turn this off? And you just hit the turn off button and just say, forget about it. So that is not good either. I'm not promoting that, by the way. So like, a lot of these things require that kind of rigor and rigorous investigative process. It's almost like digging through an incident, the actual operational security incident, and you have to do that investigative process. And that is extremely expensive. And specifically to UDAP, in this case, we also have to deal with an additional layer of human defines policy, right? So we need to essentially say, yeah, like we have to validate every single employee. Do they follow the policy or not? And like for all of those, like the effect of having a lot of logs show up is like, oh, okay, how do I know if it's I actually looked hard enough? Like, did I not look hard enough to find the right things, or did they genuinely were not supposed to do something that's bad, that's not supposed to look at this? The problem with that, the reason why that's important is that, like, yes, it's okay to find whether or not a particular person violated the policy, and then it's actually easier to find when they didn't violate the policy, because it's like, oh, I already see the particular reason. But how do I know they didn't? It's kind of like, I remember my advisor back in the college school, he would tell me, it's like, it's really easy for you to prove to me that you have $1 million, but it's very hard for you to prove to me you don't have $1 million. Try that. Because I would keep on saying, oh, you were just hiding an offshore account. You have it under your mattress. You could be like, that dichotomy actually manifests in these kind of setup. So at what point do you stop, right? Asking those questions. And so, and then the other part of this is that we have a matter of making sure we need to be able to trust the decisions that come out of any kind of automation that goes through this process. And that's something that is very difficult to attain in genuine probabilistic systems like applied ML systems in the past. All right, like I said, we have already tried a bunch of these things, and then many of them are actually just manifesting in the results we saw earlier. But we try to dump all the logs into context. Just fix a time window, fix a few like, all the activities by a particular user, and see what happens. Yeah, that didn't really work. The context window exploded in cases where it just literally went over the context window and gave up. And they also all basically garbage, because most of the log that's put into it are irrelevant to the context of the policy decision. All right, and then we do the classical temporal chunking. So looking at a series of logs in sequence based on timeline, and chunk them 100 or 1,000 at a time, and then put it into the context window, and progressively summarize along the way. Well, the problem with that is, A, the information the relevant needles in these haystacks, right, could be farther apart than being right next to each other temporally. And two is that, like, a lot of the important pieces of information through summarization actually gets erased. It's generally considered as called a form of erasure, information erasure. And if folks are like really into information theory, I'd love to talk to you about those as well. And then the third way is through RAG. You can build a RAG layer on top of your logs and then try to query through like a RAG setup. Well, there's a problem with that too, because like it's not necessarily precise, and then it still can lead to fragmentation because you can pull back the wrong things, because the top n is still a relative form of that. You don't know what n should be. And two is that the semantic relevance from the most RAG setup, like through vector search, a lot of times not actually even relevant for your log data at all. Like, try to run log data and semantic search, you will show a bunch of similar looking logs, yes, because they come from the same log source, but not because they're actually informationally like relevant. And because no matter how well you build these systems, RAG are still using a similar kind of setup in the back from an embedding perspective, right? All right, so I talked a lot about problems, and there's plenty more where that come from if you're interested. But like, what do we do? So we can talk about solutions real fast. I think like one of the key things in realization when it comes to these kind of applied LLMs use cases is that when the paper originally, which LLMs are based out of, the attention is all you need paper from Google back in 2018. Like, I'm trying to basically imitate that. It's like, for agentic purposes, like the right context is all it needs. So, and what makes a context, what makes that good is that a context is good if it's concise and precise. So a concise context is short, like ideally, right? As short as you can be, right? So information dense, that is conciseness. So we want to increase the signal to noise ratio that I mentioned earlier. And precise is that every single piece of information that you do put in it, it is actually relevant to answering the question that you're trying to get the agent to answer. And I will say, all this is easier said than done, right? And also it's not all it. Sorry, I had to quote the all you need part. Because it is not necessarily just that. Yes, from a agentic context processing and management perspective, that is all you need. But like, how do you even define what this right even is? I'm in the organization somewhat known as a stickler for definitions these days. But like, I sound like a broken record, but being able to clearly define your goals and then have a very crisp definitions of what you want the agents to even do is actually really important. And then this is the part in which a lot of people think they have it right, but they don't actually. And interestingly enough, the 2 points you want on that too is conciseness and preciseness. And like, I'm gonna go a little bit on a tangent here in a related way. Like human like language is inherently, I would argue different languages have different levels of this, but like human language, which is how we interface with LLM agents, right, is inherently extremely imprecise. We have to, I think that needs to be something we need to really sink in here. Like the modality in which we communicate with the agent in of itself is not precise. Like I should have actually pulled up like my linguistics teacher back in the day actually showed this really interesting 7-word sentence written exactly the same way, but if you change your emphasis in terms on which each one a word, you get 7 completely different meanings. The agents are not hearing your intonations. They're just reading, right? So I think there was an earlier talk, I had an example where it was like, oh yeah, don't change the configuration, and it just deleted it. That is another example of this impreciseness of our definitions. So if you can get your definitions and your goal setting to be extremely concise and precise, you will have a hell of a lot better time when it comes to the effectiveness of the agent. So how all that manifests is we had a hypothesis that if we actually, instead of using language as the primary medium, like just words in sentence structure, as a primary medium for managing our context, but instead use a graph as the working memory, like that will potentially stabilize the context window problem for us. And essentially, that's what we did. So basically, we build out the context in a progressive manner, in an iterative manner. And we pulled let's say we start with one event that is something that we're interested in looking at. And we progressively look at, oh, what are the entities that this particular event is describing, and what are the relationship between them? And are the relationships causal, and then what type of, how might that actually manifest? And then we follow those relationships and start progressively searching our databases for additional information to enrich. So I'm going to go into this a little more detail in the architectural discussion. But this is a method in which we will be able to then essentially construct what are truly the relevant contexts to then feed into another system for making the judgment call. And there was a video, but not exactly displaying. We can get back to that later. Yeah, the video is actually a recording of the prototype of the agent actually doing this in action in a very visual manner. So yeah, wanted to give a preview of that before I talk about architecture, but we can get that next time. So architecture-wise, this is roughly how a very, very high level, how it looks like. right? I tend to talk through this a little bit. We extract the entities and relationships, and we do the enrichment. We then do the graph construction, which is actually all intertwined. And then we do this loop over and over again until we get to a point in which we are comfortable that all stones have been turned. And this kind of iterative kind of exercise, it requires essentially a graph agent to constantly go to the log sources to iteratively search and then configure what it needs to look for across the board. And then it updates the graph working memory, like I mentioned earlier. So that way it can actually be able to take that working memory and then give it to the business justification agent. And that business justification determination is the part in which I'll talk about in a bit. So the first is entity extraction, right? Like you have a log. How do I extract out an entity? This is like the good old days of using name entity recognition, NER, and any ML folks here. Like, yeah, Dan. LLM actually does this fairly well, surprisingly. So, well, not surprisingly. There's deterministic ways to pull it. So use your schema and predefine like different like descriptions of the fields. You can use regex on the logs and then just pull all of those. And you can also use LLM-based unstructured text with few shot examples to also pull out the relevant information. But what we found to be the most common and useful is a combination of like the two in a hybrid manner. So having a structured extraction, because like logs are, again, I mentioned earlier, LLMs are not necessarily that good at reading logs. So if you can actually pull them out into digestible chunks that are actually reasonable, deterministically, do so. Like, I love determinism. This we're coming from an ML guy because we live in non-deterministic world. But like, where I can find determinism, I will love it, I use it. But within those kind of deterministically extracted things, you oftentimes will need to do, there's still unstructured text inside of it, right? Like, for example, command line prompts. So you may have like a logging that's already structured, but the command lines are not parsed, correct? It's just straight string. So do you build a custom parser for that, or just let LLM take a rip at it? LLM does a fairly good job there. And once you have that, then what we do is take those entities and relationships and progressively search the data sources. And in this case, our data sources are logs and other internal tools and all of that. So like something like, for example, John viewed D12345, like actually, I messed up that slide. But what it's supposed to say, my bad. What it's supposed to say is that, okay, like, who is John? And then can I search that, search more about John, like this particular person? And then like in like D12345, is that a document or is that what type of file, what kind of information is it? And if it's a document, we go read it. And the power of agent here, contrary to the standard just pure ML approach than before, is that we can actually read the contents of the documents. And then we extract progressively. Again, that becomes a node, right? And you then traverse and progressively retrieve. And so through that exercise is how you ends up with this graph. And like I kind of just described this, but essentially you're pulling all that content. But then a very important piece is pruning. Not all the things that you retrieve in an entity relationship extraction is actually relevant to your particular task that you're asking the agent to do. So an important part of the graph construction process and the graph agent's task is also decide which ones are not useful and get rid of them. This is how you increase the signal to noise ratio. And then you iterate, just keep going, right? This is just good old like PageRank style graph traversal algorithms that we used to learn in school. I don't know if we still do that these days. All right, and then then you have a determination step. This is the business justification agent portion that I mentioned earlier in the architecture diagram. This is where it takes the existing graph context that you have in that graph working memory and then try to make a determination. Is this justified? Have I already found the justification for this? And if you did, okay, we can stop. This is good. Like we don't need to keep on crawling through all the petabytes of data over and over again. But if we haven't, like, okay, maybe we need to go back. But how many times do we need to go back for? Becomes a question. And in our case, this particular use case, we use data to determine how many exactly iterations do you really need in order to get a good result, which turns out to be about 3 steps away from the original inbound, if anybody's interested. It's kind of like this, the 6 degrees of Kevin Bacon. I'm not sure anybody still remember those. Yeah, actually exactly half that, which is kind of funny. Cool, I'm talk about results. The methodology in which we run this is we run offline and online evaluations. I think evaluations are key when it comes to trust of the agents and believe that it actually works. It's ways to prove ourselves that it actually works. So what we use is a combination of real world and synthetic examples of both positive and negative cases. So in UDAP, for example, will be policy violations versus non-violating events. And then we measure precision recall and false positive rate across that. And we also use the compressed context effectiveness measurement. And that's where we compare like what the working memory essentially looks like to what a human investigator that have done investigations before and what they thought was the correct set of events that were relevant, and compare the two together using IOU, intersect over union, not IOU money thing. So based on those methods, we essentially get to this kind of actually measured outcome. So generally speaking, the amount of context that it needs gets reduced by 16x, and that's a lower bound number for the most part. And so we can basically turn like tens of thousands of logs into just a few hundred logs that's actually relevant for your use case. And then performance measurements against baseline. Baseline is where we have an agent just dumped with a temporal chunking. That is the baseline. We have achieved near 100% recall. Recall means that whenever there's a true incident, you actually catch it. So basically, we never miss. And then on top of that, we include the precision of our system. Precision is when the model says that it's a true positive, what's the percentage of that is actually true positive? Or like when your model says this is a positive outcome, like how many times do you actually write about that, essentially? And then so we increase that by an order of magnitude. And then there are many times in which our original baseline agent was basically unable to make any determination whatsoever because the context window just exploded. And so in this case, the graph power agent was effective on greater than 75% of the most difficult use cases for those. All right, and I think the why it works probably is rather self-evident. Like first and foremost, it preserves the relationships, the contextual relationship between things, right? Rather than just using a random time-based thing which is polluted with a lot of noise. And the fact that it's context and task aware when it's traversing and pruning the context graph, essentially, is another piece, because otherwise you wouldn't know what's relevant or not, like if you just train a classical model in some cases. Agent context in this case ends up being well, relatively speaking, it will become like multiple orders of magnitude more concise and precise. And another really important benefit of it is the decision process is actually explainable. Because remember that justification, like determination agent being separate from graph agent? The determination agent's input is just the path in which that particular traversal went through, right? Like it's given the context of where the path has went through. So, well, you just need to surface the path as the justification, like causal decision timeline, essentially. So a lot of lessons learned too, but I'm going to try to kind of distill into a few key points. Contextual information, in terms of looking at the information and logs, is better than just temporal. I think At this point, hopefully I don't need to explain why that might be, but that preserving contextual relevance is actually really important. Hybrid parsing actually worked, performed the best out of all the different combinations, and that is partly because our logs are just not the most perfect clean thing out there in the world. And as we apply the online, so I didn't really mention the online way in which we did this for evaluations, which is we actually live run this in parallel in shadow mode against human investigators. What's fascinating is that the agentic process in which it does that iteration, which is, I wish I can show you the video because it will make it so much more obvious like how this, why this part is true, is like the agentic process ends up imitating the human investigative processes of keep on like exploring and like contracting, exploring, contracting, kind of like exercise. You go down one path, that didn't work, okay, go back, backtrack, try another one, right? That actually is exactly what the agent does when we visualized it in a visual form. So there's a bunch of challenges, of course. Like, how do you even determine what is considered like a correct or noisy entity like in the context of this, right? When the agent's traversing, like, how does it make that determination that it is the correct thing that I should keep on looking at versus not? So for this, we actually ended up using a number of things like graph metrics to measure this. In classical NLP world, we use things like TF-IDF, term frequency, inverse document frequency, as a, it's actually still a very powerful classifier, by the way, despite all the LLM hype, and super cheap to boot. So we use the same kind of technique on the graph as well to essentially get that sense of if something happens a lot, like a node has a ton of connections to it, it's probably less important than something that's fairly unique, like from an information perspective. And the LLM reliability across different formats of logs is also limited. There's an active work on that we're trying to figure out, but like it doesn't always work on every single type of log, by the way. It works. It also doesn't work on every single type of command. And how do we balance between the completeness versus we're just overloading information? And while we have some solution, it is not necessarily fully generalized to every single use case we can think of. And latency from procedural generation, what you notice what I just described as a very iterative process, right? And that takes time. And it also churns through a ton of tokens, which is not ideal when you're budget constrained. And lastly is trust with automation, like just general trust about the system from people. So as the key takeaway of this talk, like I think the main thing is context, like keeping it concise and precise is key to effective AI agent usage, especially in the log analysis world. And graph traversals as a generalizable context management tool is actually fairly useful. Like it's able to show the results are what's described and benefited from this, right? And continuous monitoring, evaluation, and feedback mechanisms is actually how we keep the system healthy and trustworthy. So that part is really key because otherwise, like the system won't, you can turn it on, but then nobody trusts it, then nobody will rely on its outcomes. So I have a minute left, but then like generally speaking, the next steps is about generalization. So the other original video I want to show you was actually a prototype out of this, where we're trying to expand it beyond just a policy validation type of use case, but also other kind of security use cases too. The video was run against infrastructure security logs instead, and do infrastructure security incident investigation and remediation. And more intelligent expansion pruning and reasoning capabilities. This is what I mentioned earlier. It's like, how do I decide what is relevant versus not? Like, and how do I be more intelligent about the path traversal? This is something that we can take I used to do reinforcement learning a lot. So this is a common problem in Monte Carlo research type of setup in the past. So we're doing those kind of exploration right now. And we're also looking to build a unified graph abstraction layer on top of all of our data. And this is to help combat with the latency problems and how much we don't have to reconstruct every single time. But instead, if there's already pre-extracted into a graph, then you can take that part out of it and then have the agent focus on the reasoning capabilities. And I'm exactly at time, so thank you. And any questions?